Okay, so this week what we're trying to cover would be again still something relatively simple. Specifically, we're looking at what type of models that what type of methods that potentially we can start sometimes, and then we want to introduce least square method to choose the best model. In other words, not only least squares, potentially we could look at performance metrics that we can use to choose the best model. So here is the rough agenda for this section, which is really for Unit 3, and then it includes fitting models to data graphically, analytical methods of model fitting, and applying the least squares criteria to be the one of the method for the model selection, and also how to choose the best model. Okay, three major tasks when we start analyzing a collection of data. Um, First of all is we need to look at fitting a selected model types or model type or types to the data. So we have to find out what would be the best model, and then what would be the criteria potentially we could use. And then we can choose the best appropriate model from competing types that have been fitted. So a specific criteria that has to be selected. So in this case, the first bullet there is really saying that we discussed methodologies such as simulation, statistics, or math models, and then which model would be which type of model we should be thinking of. It could be a simulation, could be an experiment, could be a math model, could be some sort of abstraction or statistical analysis. So that would be the first thing that usually we would need to think about. The second thing here we are trying to see is once we define a specific type or types of model approach that we're going to take, and then you have to figure out which would be the appropriate model, which model potentially could be better. And then the third one here is saying that making predictions from the selected data, and then specifically also a performance metrics that you have to be established to determine which prediction model is working better. And then in terms of the general process in the modeling process, we have multiple potential areas that we could have some sort of error, including formulation error, just in case that we just take the wrong approach. We made wrong assumption, and the conclusion as a result could potentially be mistaken. The second potential error would be truncation error or round-off error, which is the third one. Majority of the time, the second and third one are less of a concern unless we have a lot of accuracy in between, such as if we think that we leave 6 digits after six significant digits, we still don't feel comfortable, and we think potentially still have runoff error, then essentially that indicates that the accuracy or precision of the specific model requirement of that model is really high. And then the fourth type of error would be measurement error. That would be when we collect data, if we know some certain variables or attributes has potential risks of being more prone to error, then we should pay attention to those metrics. And then in this case, I really want to mention that in many cases, you have to look at your data, try to understand what's happening, and try to correct some of the errors if possible. Just give you some specific example. If you're trying to build a prediction model of credit risk of a certain consumer behavior, right? For example, a lot of people are trying to apply for a credit card, and then they have a variable that is FICO, and then usually if we know it should range somewhere between I would say 400 to 900. But if you see some indication, if you see bunch of if you look at the distribution of the FICO of the dataset, you realized that uh, you found out that the distribution is really not from 400 to 900. You saw a lot of 40, and then 40 or 550, 55, for example, if it's 55. And then the question becomes, what do you believe? Could that be an input error? Could it be really meant to be 550? So some of these situations you should use your judgment on a specific data set or variable, try to correct them as much as possible before you before you build any model. I think that's a really important process in this process. And we know that if we purely just look at visual fitting, then fitting some sort of model to the data graphically, we potentially could be running into the risk um, of issues. Of course, the famous example would be overfitting. We would have some sort of example shortly to illustrate that. And then as a result, many of times what we do is we do some sort of this data transformation. And then if you have exposure to linear regression and logistic regression, you would realize that doing some sort of regression, doing some sort of transformation, you would be able to translate a specific nonlinear relationship into a linear relationship, so that it is easier to be represented statistically. Okay, so I want to look at the one of the example, which is called the Chebyshev example approximation criteria, which is in the textbook on Figure 3.12, and and then I also want to point out that the model itself is modeled as a minimization problem, and it is really a linear program. And then linear program is something that we would be we would discuss in chapter 7. So in terms of solution methodology, at this point, I don't think you really know, but at least you would be able uh, to um, to know how we formulate the problem. And then on top of that, we also want to discuss a little bit on the least square criteria. So bear with me a little bit. Let me try to open the textbook. Okay, so here it is. I think you should be able to see my screen. Let me zoom in a little bit more. So here is an example that I really want to get into a little bit detail here. So for example, what we want to measure the line segments of AB, BC, and AC in this figure 3.12. Assume that your measurements have three estimates. It's AB is 13, BC is 7, and AC is 19. So we know that AB plus BC should be AC, which should be 20, but your measurement of AC is 19. So as you would expect in any of the physical measurement processes, this discrepancy probably would happen. So in this situation, the value of AB and BC I already discussed here. That is 20 versus 19. And then what we want to do is we're trying to resolve the discrepancy of the one unit using something called Chebyshev criteria. That we that what is that is we will assign values to the three line segments in such a way that the largest absolute deviation between any corresponding pair of the assigned and observed value is minimized. So which essentially is we have this type of objective function in there, which is we want to minimize the maximum of the actual value minus the measured value, right? Okay, so that is the target, and then what we can do here is this is already telling us some sort of solution, but let's look at how this is formulated. So suppose that we let x1 represent the true value of length of the segment AB, and x2 be the true value of BC, and then we know x1 minus 13 is the residual part discrepancy between the true and the measured value. So because we know the measurement is 13, and we already suppose that x1 is a true value, so we use x1 minus 13, get R1 being the discrepancy for line segment AB. And then for the segment ABC, the second segment above, which is second segment on the right hand side, that is x2 minus 7. The measurement is 7, and R2 is the discrepancy in this case. And then we know that x1 plus x2 will be the actual value of the actual length of AC, and then use that number minus 19 to get a third discrepancy. That's original formulation, and then we can see that the numbers of those three numbers R's are called residuals. And then what we're trying to do is we're trying to minimize the three values, right? Absolute of those three values. So let's assume that we call that the largest number of those three numbers is R. If we call that largest number being R, so what we are trying to do is trying to minimize that largest discrepancy or the largest residual. That's a definition. So we try to minimize that, and then we have to subject to certain conditions. One of them being that because we already assume that R is the largest one, so R has to be larger than or equal to the R1 absolute value, or R1 absolute value less than or equal to R. And also the same thing happens to the other three as well. R2 absolute value less than or equal to R, and R3 absolute value less than or equal to R. So once we know this absolute value, that can be further expanded as R1 larger than or equal to negative R and less than or equal to R. That's equivalent, basically left hand side and right hand side, that's equivalent, so that we know those three conditions can be rewritten to the right hand side that we saw there. Okay, and then if we go to the next page, you could see that. And then next thing that here that what we did was each of these conditions can be replaced by two inequalities. For example, which is I already said R1 R larger than equal to R1 larger than equal to negative R, which is equivalent to R minus R1 larger than equal to 0, and R plus R1 larger than equal to 0. So essentially to say that this side can be one equation, and that side on the right hand side could be another equation, R minus R1 larger than equal to 0 on the right hand side, and left hand side is R1 minus R less than equal to 0. So once we have those, and if we have all of this, so essentially we would have 6 inequalities. If this is done for each condition, the problem can be stated in the form of a classic minimization problem. So let's see why. Because we know that R1 is something that we earlier we defined as x1 minus 13. So if we know that r minus r1 larger than or equal to 0, if we replace r1 by x1 minus 13, then we can get the first equation. And then similarly for the second equation would be equivalent to replacing r1 by the first condition that we first definition that we had earlier, using x1 minus 13 to represent r1, and then we get the second equation. Once we have those two, we know that for the other four, the other two sets, we would be able to have the rest of the equation as well. So now the equation becomes this problem. We call it minimize something subject to certain constraints. So this is something that we call it linear program. So why is linear program? Just because the objective function itself is linear, and then all the constraints are linear, so that we try to minimize this R. So that is a linear program. And then in chapter 7, what we're trying to learn would be we use some sort of method called simplex method to solve a linear program so that we can get a minimized value of R, which has been happen to be R equal to 1 over 3, and then corresponding x1 and x2 being those two different values. Okay, so that is something that just want to introduce you to that what is linear program. Is specifically we really want to introduce you this concept of Chebyshev criteria, which is trying to minimize maximum deviation of certain segments. Of course, this particular example is only application, but it does have a lot of other usages too. So we already have this. So and then I also want to continue with this is another example in the textbook talk about how to minimize that difference. And then I want to go to the next example. That would be least square criteria. So this is another possible metrics that we're trying to minimize. For example, when we try to estimate a linear regression, if I use a specific example here, so we have certain x and y's, we have bunch of observation. As we know, the question is really that we're trying to figure out a linear line, which would be the best line. And then so question is whether the green line is better or the red line is better, right? So we are trying to figure out the best fitting line. So what we're trying to do is really that we want to minimize the actual observation value here. For example, use this example as a specific point. We want to use this y value to get the difference between your predicted value, which in in this red line would be there, and then in the green line it will be somewhere here. So what we're trying to do is we get the difference between those two, the distance there, or distance there, the second distance, distance 1 and distance 2, for two different lines. So what we're trying to do is we're trying to minimize the y from observation, which in this case is this one in the middle, and from the estimation. If we have the estimation being the red line, then that would be our estimation. So we use that difference and squared, sum of them up, every single one of them, the difference of this vertical difference, sum of them together. That's our objective. We're trying to minimize that distance. So now that's simplified explanation of linear regression. But here we know that if we use this specific objective function as our function, then we know it's a quadratic function. And then in any quadratic function, we know in order to get the minimization, we take first order derivative and second order derivative, we should be able to solve the problem. So basically, long story short, if remember, for any quadratic function, if we look like that, we're trying to find the minimum. What we do is we just take the first order derivative and second order derivative and set them to equal to 0. As we know, at this point, the derivative should really be 0. That's why this specific approach could work. So you take this first order derivative, partial order derivative of a and b, which would be the initial expected linear line, and then we set them equal to 0 so that we would be able to get those two set of equations. And then once we have those two set of equations, we could rewrite them so that we would be able to solve our a and b. And the a and b turns out to be those two, and then that would be this actually is a simplified version of linear regression, which is really the linear regression. And later we probably have a little bit of discussion on why this least square criteria happen to be the regression objective function. So of course, there's more discussion in the textbook as well, in the case that what if it's a power curve, and then we still use the same objective function using measured minus the estimated value. Fxi is coming from the function itself, and then squared, and then sum all of them up, and then we're trying to minimize that. Okay, so that is really a high-level explanation of those two, but hopefully give you good understanding of those what we are trying to discuss here. I already talked about this intro to the linear regression formulas, the least squares. Take partial derivative and then set partial derivative to 0, and then solve for the slope and intercept. And then we could also fit a power curve, which would be a nonlinear regression, because as we just saw, y equal to a powered x times x powered by something that is already powered by more than 1, which is a nonlinear. And then we could transform least squared fit to transformation from nonlinear to linear. Essentially, if you take a logarithm of the specific power curve, you would be able to translate that to some sort of nonlinear, some sort of linear equation. So usually when we try to choose the best model, you look at the fitting error, you want to compare different errors, and then you would also make considerations such as not only the error itself, but also complexity of the model, overfitting of the model, and the generalization capability of the model. These are the fundamental basics that we should consider. Of course, if you by some point you should probably already learned bias and variance trade-off between the in-sample and out-sample error, how you can make that trade-off, make sure that your model would not only be working well on the sample that you're trying to model, but also it can work really well on the out sample, and it has generalization capability. Okay, so that is the gist for this unit, and then for module 3, we have this four homework for homework problems. You only need to select two for homework 2.1, which essentially is the first component. You pick two of this, and then for the second component, you look at chapter 4, pick another two. By the way, probably you know, but some of the students are a little bit confused that we only need one submission every 2 weeks instead of two submissions. So essentially, I call it homework 2.1, which would be coming from here. Homework 2.2 combined with homework 2.1 together can be submitted to homework 2. Okay, so now, do you have any questions? No? Okay. Okay. Cool. Okay. Right. For 622. Uh, okay. Yeah, that. But the homework one we haven't finished yet, right? For homework. No, no, no. Yeah, I think it's 16th. Exactly. Yeah, yeah. I'll follow up with that for homework two, definitely. Yep. Okay, no problem. Yep. Okay. Um, so let's continue on this topic. So next one that we really want to discuss is something that we look at a basic understanding of simulation. So in case that you have not taken any simulation classes yet, maybe you have already, but in here, what we're trying to do is really just high level discussion of simulation, what it is all about, and how we can leverage some of the approach. Specifically, we kind of limit ourselves to something called the Monte Carlo simulation. So first of all, before we start, we really want to mention that why do we want to talk about simulation? Rationale for simulation is when we are not able to construct an analytical model, meaning that we're not we think that analytical model is either too complicated to construct, or even if you construct some sort of analytical model, it cannot represent the actual behavior. So in that case, we have to build a simulation. And then the second possibility would be we realize that the insufficiency of building a model, and then you realize we could use simulation to obtain extra data to support our analytical results. That's a second possibility, and then the third possibility would be other than other approach, there's no way that you would be able to help to justify the results. Then you only possibility is you can use some sort of simulation, and then here. Okay, and yet another thing that is, it could be use a probabilistic model to represent deterministic behavior, or the other way around. You could use probabilistic model to represent probabilistic behavior as well, and potentially you could also use deterministic to represent some sort of probabilistic behavior. So that is something that just keep in mind. And then let's look at this example. So what we're trying to do here is something called area under a curve, right? So in college calculus, you know that we could use integration to get the area under a specific curve if the curve itself um, is is analytically tractable, in the sense that if it's x squared and then we want to get the area of the curve, we could use integration to the range of x and the corresponding curve dx, and then integration to get the area under the curve. But the thing is, what if we don't know the function? We don't know it's x cubed, in the sense that we know a certain shape here. It could be a sine curve. It doesn't look like exactly a sine curve. And then the question becomes, is there a way that we could simulate? Okay, so one approach here is, yes, absolutely, we could do the simulation, and then what you do is you start with n random points to be generated in the simulation. This n could be really large. Suppose that you have 10,000 points that you could generate, and then this 10,000 points you would have for each set of point. For each point, it have a x coordinate and a y coordinate. And then suppose that the first point you generate is x1, being this point P, and then it has a specific x and y, and then you know where it should lie on the graph. And then what we can do is we use the function fx. That's one way. Of course, I already mentioned fx probably is unknown. It's really known, but it's not easily tractable mathematically. Or even if it's easily tractable mathematically, we could still use this to support our integration output, right? So you could then let's do one thing. The second output is we want to get the area. So what we do here is we start initialize counter equal to 0, and then for all the i's starting from 1 all the way to n, do step 3 to 5. Step 3 is calculate random coordinates x and y that satisfies x is between a and b and y is between 0 and m, and then try to get this x, because we already generated xi, which is x1, suppose starting from the first point, and then you can calculate fx1 to get whether the fx1 is what's the fx1 value, and then you can use your y, the generated y value, which is y1, to check whether it is less than or equal to fx1. If it's less than or equal to 1, essentially says that it is under the area, under the curve. So that what we can do is we increment that counter by 1. Otherwise, we don't increment that counter. In other words, if this calculation is here and less than the calculated, once we generate a point, the y1, if it's less than fx1 corresponding point on the curve, then we increment that counter. Otherwise, if it's somewhere here, meaning that this condition will not be met, we generate a point, and then that y1 is larger than fx1, then we do not increment that counter, right? So once we do that, keep going until all the way through 10,000 points, we realize that bunch of points are here, bunch of points are here, bunch of points are there, and then use all the points happen to line underneath the curve divided by the total area, then we would be, which divided by, instead of total area, in this case we only sampled 10,000 points, we should be dividing that number by n so that we can get the area for this percentage of the area for the area that is under the curve. In other words, what I'm saying is contour divided by n is the percentage of the area that is under the curve and times the total area that we know, which is m times b minus a, so that we can get area that is under the curve. So in this case, we would be able to output that area, which is the simulation output. So that is one way to look at simulation. And the next example that we have here is very similar as well, except that it's three-dimensional space. We were saying that how about volume under a curve? And then instead of generating a point with x and y coordinates, we need to generate a point with x, y, and z coordinates, and then we need to test whether the point is under the curve or above the curve, and then if it's under the curve, increment the contour, otherwise we don't increment, and then at the end we use the proportion. Again, the proportion contour divided by n times the total volume that we have in a space that we were looking at, and then we could output the volume that is under the curve. So that is the second example that we have here for simulation. Here, I also want to introduce you something that we call random numbers. In simulation literature, there is nothing real random. That's why we call it pseudo-random. There's a reason that we call it pseudo-random, just because that it's either it's usually the random number with the cycle, depending on how good the methodology is. It could be the case that it cycles every 10,000 points or every 5,000 points. So the reason that we call it pseudo is just because it has cycles. It started repeating after a certain point of time. So it's really not random, in a sense that because after certain points started repeating, then it's no longer random. So that's why usually what we're trying to do when you design a specific random number generator, we hope that the cycle is long enough so that it doesn't started the cycle very quickly. So one of the methods that we want to introduce here is something called middle squared method. So it's something that we start with a 4-digit number x0, call that the seed. So in random number generator, anything that start as the first initial number, that's called seed. And then what we do is square it to obtain an 8-digit number, add a leading zero if necessary. In the case that we're not able to get 8-digit when we square the 4-digit number, then what we do is we add extra zeros at the beginning so that we can make sure that it becomes 4 digits. And then we take the middle 4 digits as the next random number. So that is one way to generate. So the approach itself is simple, so I don't really want to go to the Excel or anywhere to test. I think we do have some homework that you could work on this in R to see the cycle behavior that I just discussed. And then another approach is something called linear congruence methodology. This is to say that the next number is hinged upon the current number plus b, a times current number plus b mod by c, and then a, b, c are constants. And then in this case, c is something called modulus, a is a multiplier, and b is the increment. And then in reality, you have to pay attention to the possibility of cycling, and then the lack of independence among the numbers in the list of random numbers. So here I don't really have a specific example for you, but as you can imagine, with the right selection of A, B, and C, you possibly that you have a very different cycle for the random number generator. And then here that previous two examples that we discussed in terms of simulation, is really on the deterministic behavior, because we're looking at the area under the curve, area under the volume. But here we're talking about something probabilistic. To say that, how can we simulate some sort of behavior like that? One of the examples that we use is a flip a fair coin, or roll a fair die, and we can also look at roll of unfair die, or a pair of unfair dice. And then the reason that we introduce random number generator here is just because when we come to this situation of probabilistic behavior, we have to leverage random number generators, because every single realization of actual number is coming from based on some sort of random number that you studied. So that's really the key that it has to be part of the simulation. So now let's look at this fair coin example. Suppose that we have input is total number of n random flips of a fair coin to be generated in the simulation, and the output is the probability of getting a head when we flip a fair coin. So it sounds like it's actually simple, right? You do a test, you want to run 1,000 times, and then the first time you just check whether it's a head. If it's head, your counter should be counter of that coin should be incremented. Otherwise, you don't increment. But the problem is here is in the simulation space, we are not able to be precise to say it's a head. We can do an experiment, but in simulation we are not able to. We don't know if it's going to be a head or a tail. And then what you do is you generate a uniformly distributed random number between 0 and 1, and then you define anything between 0 and 0.5 is a head, and then anything larger than 0.5 is a tail. That way you would be able to simulate the process. So you obtain random number. If it's between 0 and 0.5, you increment that counter. Otherwise, you don't increment that counter. And at the end, the head would be the counter divided by total number of points you actually generated, which is essentially total number of flips that you tried, or total number of tests. Okay. So of course it becomes a little bit more complicated. In the field dice example, it's not quite yet. In this example, we would still think that it's kind of comparable if the x is between 0 and field dice, because we know it can have 6 different output. So each of them should have 1/6 probability, and then in this case, we would say that if it happens that that random number is between 0 and 1/6, then we say that counter 1 should be incremented, and then we can design 6 counters, and then use each of the counter I divided by total number of throws. We would get the probability of the specific number that we are looking at. Okay, once we know the fair dice, and then the question becomes a little bit more complicated. What if it's unfair dice? Then what you do is, suppose that we know there's certain probability that it belongs to, you show up as a 1, have 10% probability, and certain probability of 4 has like 30% of probability you show up as a 4. If that happens, then you can still do this to design that threshold, so that we would be able to calculate the probability of each of them. Okay, That's a second. There's one more example for how to simulate a probabilistic behavior for unfair dice. And then at the end of the chapter, there's a section specifically discuss something called the inventory model. We really don't really spend a lot of time here, but just want to give you a sense why it is important. For example, in Walmart, what not Walmart, let's say use Target or Amazon as an example. Maybe Amazon is better. So what they do is the specific items that Amazon have. Not majority of the time, it could happen that it's not something that actually Amazon has inventory. But this specific example that I'm trying to explain is it's something that Amazon does have some sort of inventory. And then average daily cost for them, it could be they have to put something in the in the warehouse so that it is a storage cost. And on the other way, on the other hand, they have to deliver once there is an order, so they have to incur some sort of delivery cost, as well as demand would be a function of the daily cost, because there is a potential risk of if I only have even two of the items in the inventory, but I would have full demand today, and two of them actually I was not able to fulfill, then that would be some sort of cost as well. So average daily cost is a function of storage cost, delivery cost, and demand rate. So in the inventory model, so we have to make certain assumptions such as the demand levels and the frequency of the demand, or even the arrival of demand follows certain distribution, and then I also want to make a point here, that is some of the assumptions that we make could potentially be the results from analytical models, such as I just mentioned for the demand arrivals. In many cases, we actually try to model the demand arrival being a Poisson process. In other words, the inter-arrival time between this demand versus previous demand, it follows exponential distribution. So in that case, why are we able to make that assumption? It's just because based on analysis of previous demand arrival time, we are able to analytically um, to uh, to to fit that interarrival time being exponential, or the demand arrival being a Poisson process. This is actually not unique. It's something that happens everywhere, such as the arrival of cars into a specific intersection. That's one standard way to think about it. It's a Poisson process. The number of arrivals going to a specific intersection, and then the number of arrivals that actually cause giving a call for a call center. The number of arrivals of the customers calling a specific call center can be modeled as a Poisson process as well. So the bottom line is you model that as a Poisson process, and on top of that, you can build a simulation model to get this average daily cost. And then it could happen the other way around, meaning that the simulation could be the input of your analytical model. If you have certain variables that you have to simulate to get a better understanding of it, then you could use simulation as sub-model for your analytical model. So that's really one of the points I want to point out here. So high level, it's really for this particular Monte Carlo of the inventory model. It's just how we could look at the inventory of the company, and look at the demand, look at the replenish policy, and think about how we could simulate this whole process so that we could have a better sense of what type of replenishment policy that we should use. And then, which is really this last section that we want to hold on 1 minute, 1 second. Okay, and then last section that we want to discuss here today is something called queuing system. Um, so the example that was used in the textbook is something called a harbor system, and then a harbor system in terms of the whole system in near the harbor, and think about how we could use a simulation to look at it. And then I want to use an example of the checkout counter of Target. So the question becomes the specific approach that we call is MM1Q. So M meaning that inter-arrival time is exponential, and then the arrival process is Poisson, and then the service time it takes is also exponential, and then the service process is something called Poisson process. So that is M/M, and the third one is called hold on, let me get the first M stands for the arrival process, and second M stands for the service process, and then the third one stands for the number of servers in the system. So assuming that in a target you can use MM1 to model specific checkout counter's performance, and then what we can do is analytically we would be able to get a sense on average how long it takes for a customer to stay in a queue, how long it takes for the customer to get serviced, and how long it takes for the customer to stay in the whole system. But there is certain assumptions here. That is to say that when I'm being a customer in Target, when I saw that my line is too long, I could go to a different counter. So for this type of situation, we would not be able to analytically solve it. So what we do is we use simulation. So in that case, simulation becomes handful. And then actually on the other hand, in the notes, you would see a section. I have a specific link to further give you some introduction on this queuing problem. And then many other models, morning rush hour, multiple server queues, and then it can be used in supermarkets to estimate how many servers or checkout booths might be needed. So that is another way that we look at this issue. Again, this is really a simple explanation of something called stochastic process. It involves the queuing methodologies, and it could be very involved in the sense that what if the arrival process is no longer Poisson, and what if the service process is no longer servicing time is no longer following exponential distribution, things in that nature. So it would have a lot of variabilities, but at high level, that's what it is, and it can be useful, and then it can be used with help with the simulation together, either analytically queuing model or simulation of the queues, you could have a better understanding of this type of stochastic behavior. Okay, so this is this section. This is a homework. You can pick 2 out of these 5, and then put them together. Submit homework 2. Any questions from you? Okay, so if you don't have any questions, I'll just stop here, and then feel free to let me know if you have any questions through the through email or Slack or Blackbox system. Thank you.